Hi, this is Chris. Today I'm going to talk about a presentation I gave at SPIE Advanced Lithography called Know Your IQ, Understanding Image Quality in Advanced Photomask Applications. The authors of this work were myself and my photronics colleague, Mohammed Ramadan. So the first question is, what is mask IQ? So I try to give a general definition here, and I'll read that straight. The level of accuracy with which a total mask side imaging process captures design intent. It's a shapes-driven definition, which means we're talking about the pattern fidelity of a 2D shape, for example. Could be line patterns, could be anything, but really what we're talking about is how well does the mask making process from data prep all the way up through patterning and etch capture the fidelity of the pattern, and how does it match to what the pattern designer intended. I think this also accepts the reality that the mask never looks exactly like the design. We all know that, especially Manhattan type geometries always have rounded corners. Generally, the mask process is high patterning resolution, but can't really reproduce shapes exactly as intended. So what do you do with mask IQ if you know what it is, or mask image quality? You can apply it in various ways. In mask and wafer process co-optimization, I'll give some examples of that. On the mask making side, you can use it in mask matching, assessing mask manufacturability, cost, and speed. You measure it, at least for the purposes of this talk. It's determined by direct measurement. We're going to use the contour, the 2D contour of the shape, as you see on the right in red around the mask features, as kind of the defining characteristic of mask image quality. And if you have a calibrated model, you can also, of course, generate mask contours or mask image quality using calibrated simulation. So generation of mask shape contour, most accessible output. Once you have that, you can vary in various ways, quantify the numerical character of this contour, mean square error, PSD, edge placement, and things like that. So that kind of gets us framed on what mask IQ or image quality actually is. So as far as our company, and I think people in the industry have similar experiences, we've been using some form of mask IQ in actual mask production since 2016. And this gives an early example of that. What you see up on top are wafer images, wafer maps of yield. This happened to be for a memory device. And where you see the green patterns, those are good die. Where you see the red patterns, not such good die. And what was happening here in this case is, if you draw your attention all the way to the right, to the left, M1, you see some number of good die. Then going all the way to the right, M4, you see a larger number of good die. And what we were trying to do with this customer is understand why the first two masks, mask 1 and mask 2, presented very different yield characteristics that really weren't particularly good. And mask 4, which actually had a poorer mask specification, conventional mask specification, produced actually much higher yield. And we measured it lots of different ways, and we were able to correlate the yield directly to these mask parameters. So that was the interesting question we tried to answer. And we measured lots of things, linear CD and all kinds of other parameters, couldn't quite figure it out. So then we went into some of the critical areas inside this bit cell, and we started looking at shapes, particularly the contours of shapes. And you see that where I showed the SEM image here of what one of these patterns look like. We extracted a contour. This is what the original design looked like. And here's the overlay between the extracted contour of the mask and the design. So once we looked at that, we said, oh, maybe there's something interesting going on with these contour shapes. So we then looked at that on case 4, and sure enough, that mask didn't have the best conventional specs, but had the tightest and most accurate reproduction of the mask shape, and that's what resulted in higher performing yield. So we fed that back to the user. They redid their OPC and other RET things they do to try to make the overall patterning good on wafer. And you see here the difference. So when they were using just design-based simulation, that is, they were assuming the mask was perfect, they saw a depth of focus that looked similar to this blue line. When they started to look at their depth of focus with a true contour-based simulation, that is, they started to capture mask image quality in the analysis, they saw a very different result. And by this, we concluded that in this case, 2016, we had to start measuring shapes and contours, reporting those to the wafer user, and having them retune OPC models based on the actual mask shapes instead of the ideal mask shapes that were represented in the design. So then we started to apply this because it was quite powerful across lots of different projects. What you see here is using mask image quality or contour-based assessment in MPC or mask process correction. We're able to use these metrics to clean up mask patterns to get better image contours at wafer. What you see on the right is a similar exercise where we used mask image quality of these shapes to improve the LCDU or local CDU performance on wafer by almost 26%. So we kind of got a little bit excited about this idea that there's a tremendous amount of information and power captured in these 2D shapes as defined by these contour patterns. Here's another example where we used image quality or mask image quality to understand what was going on in EUV stochastics project. This happened to be with IBM. And here we were doing basically trying to predict defects in EUV imaging and lithography by just looking at the design, looking at the mask, and then looking at the wafer and seeing if we can connect the dots through simulation between what we saw in the design, the mask pattern, and the wafer pattern. So two things to note here. One is when we ran the straight simulation with the perfect mask pattern, we looked at the simulated output. We did not see these kinds of errors in the wafer pattern. When we use the actual mask contour, and now we're comparing this design to this contour, and we ran a contour-based or mask image quality-based simulation, we were able to identify defects in the pattern, and using the mask contour really clarified the role that the mask image quality had in that. Once we knew that, and once we could build a model around it, we were able to generate ideal targets that allowed us to find a set point for micro bridges and line breaks that allowed us to produce good yield. So once again, it's an example where capturing the real image quality or the contours and 2D structures of the mask, although the effects are subtle, they turn out to be quite important in the patterning effects. One more example, just to show how we've used these image quality metrics for mask and optimization. This one is a little more subtle. In this case, we have a design which looks like you see here in this pattern. This is a rendered mask. So this is what the mask pattern looked like from that design. And we were interested to understand, okay, in source mask optimization, if we optimize the source in the litho tool using the so-called perfect mask or the ideal mask or the design-driven mask versus what the mask really looked like using a contour-based model, would we get the same optimum source? And actually, you see very different sources that were recovered after SMO when we use a contour-based representation of the mask versus the ideal mask. And if you carry that forward to the right here, you see edge placement error, EPE, in the predicted design using the design-based metrics and source versus the contour-based metrics and source. So once that source was re-optimized for the actual mask image quality and mask contour, we're able to get, in this case, 4% yield fallout versus 11% fallout for the purely design-based. So again, another example where the coupling between mask image quality, as measured here through contours, and doing source mask optimization had a very, very substantial impact on the end result. So simulation, which I mentioned a few times in those examples, and image quality definitely go hand in hand in the following way. We need this image quality information, particularly 2D shapes-driven content on the mask, in order to build accurate models and do accurate simulations. Once we have accurate models and accurate simulations, we can then use that to optimize the image quality-driven processes. So these things kind of work in loop. And what you see here is just an example where we had some very complex shapes, curvilinear shapes in a design project we worked on. We did contouring of all these shapes. We built our image quality matrix, and then we calibrated our models, not just to reproduce lines and spaces and linear patterns, but also to be able to reproduce the 2D shape character of these mask features. And we were able to get a pretty good match between that model and and what we were actually seeing on the mask itself. And what you see here are mean square errors for the distribution we used, about 600 mask measurements, in this case of a few percent, which was perfectly adequate for this application. So once we have that kind of model, so now we've taken mask image quality from a concept, we've shown how you can apply it in optimization and other things in connecting mask and wafer together. Now we've decided we're going to use mask image quality as a way to build a better, more accurate simulation framework for the mask process. And so then we're going to say, how are we going to use that framework to improve our lithography? So here's an example of that. This was a curvilinear design example. And what you see here is the design prediction. Here's the GDS mask. This is what the ILT convergence generated. And here is what the pattern looked like on litho. And you see in that spot where the red circle is, it looks pretty clean in that area. Then we took the real mask. So this is what the actual mask would look like based on a model generated prediction. And you can see it clearly doesn't have the same kind of pattern fidelity. No masks are perfect. We've already gone through all this. And we just used that rendered mask to generate the same simulation. And you see what was a perfect situation. Now we have a bridging fault in the design. So in that case, we built our entire ILT around an assumption of a perfect mask. When we did the same thing using a rendered mask or the contour correct mask, we were able to get a much better solution, a more robust solution. So while curvilinear design for sure removes some of the issues with Manhattan geometries, still the ability to understand and characterize the 2D shapes in the curvilinear mask process and feed them back into the optimization can give a strikingly improved performance in the ILT convergence. So here's an example of how you might use that. Let's say you're pretty happy with that mask image quality model. Once they're built, can you use it in other things besides ILT convergence? And here's an example of how you might use that. So one thing that's very important for mask people is to make sure that the mask can actually be manufactured before you commit it to production. People call this mask rule checking. There's a lot of different names for it, particularly when you get into very complex geometries, masks that start to push against the edges of the mask making processes or tools. This kind of MRC checking gets very, very important. The problem with MRC is generally it's all geometrical based. You have a rule, a table of numbers, minimum spaces, and how far apart corners are, contours, and how curvatures are changing. And you try to check the design relative to those geometrical parameters. But when the layout gets complicated enough, it's extremely difficult to do. But now we have a very, very high quality, image quality, calibrated mask model. So we should be able to use that model to do a better mask rule check than we can do geometrically. And this kind of shows just a simple flow of what that looks like. So you have a design layer. Now we can use that model to do a writing rule check, we'll call WRC, writing rule check, to kind of capture the E-beam and patterning piece. The other piece we add on to this kind of comprehensive mask rule check is actually an inspection rule check as well. And I'll explain how we do that in just a couple slides. So we are going to take the design layer through writing and through inspection in purely simulated format to see if we have a manufacturable mask or not. So first, let's start with the writing rule check. We know we've just shown and we've published in the past, as have many others, that if you do it properly, you use the 2D contours and the image quality parameters of the mask, you can generate pretty predictive, reliable simulations of what the mask is going to look like after fabrication. And this just shows two examples of that, just overlaid simulation contours on top of the mask for a multi-beam written mask and a VSB written mask. They're not quantitative in this picture anyway, but we were able to get close enough match where we feel we can do a reliable prediction and use that model in a mask rule check. And so for that first case, this here, it's relatively straightforward. We can run the simulation we generated with the contour-based anchoring. Then we can send it through to a wafer litho simulator, and that will allow us to directly correlate the mask image quality to what's going to be a hotspot problem on the wafer. And in that way, we were doing a much more reliable, comprehensive mask rule check than just purely geometric rule checking of the mask parameters. Now, the inspection side, this is a little bit newer. Um, Here we can do an image quality based inspection imaging model as well. And what was done here is mask database. I think people are quite familiar with die to database inspection. This is when you send the database into the inspection tool, and then the inspection tool measures the mask and compares those images to the database. And you get some defect report. How well do the measured images match the database? The problem with that is when you have a database inside the inspection tool that doesn't comprehend what the actual mask is going to look like, that is the contours of the mask and the image quality of the mask are not captured in it, you can easily get overwhelmed by nuisance and false defects because the database really does not represent the mask that's going through the inspection. So how we handle that is we do our own pre-rendering step of the mask image database to capture the actual image quality and contours of the mask pattern. So there's two simulation steps in this. One is first you model what the mask should look like based on your calibrated contour model. And then you run a simulation of the inspection capture to see where the inspection hotspots are going to be. So the inspection modeling is a little trickier because not as much is known about what's going on inside the inspection tools. So we use the deep learning approach to kind of reverse engineer the imaging model going on in the inspection tools. And then we ran those cases. So now we're doing in sequence writing image check and then inspection image check to see where inspection problems might be. And here you see a fairly complicated design, and it was able to flag areas in this where we can expect we're going to have fairly difficult problems inspecting this mask purely in simulated end-to-end format. So something else we can do with this, if we have this inspection model, and as I mentioned, if you just send the design database into inspection straight, you can get a tremendous amount of nuisance defects, especially on very, very complex designs. However, if you pre-render that database with the actual transfer or smoothing function of the mask making step, you can dramatically reduce those nuisance defects. And so this just shows that example here. It's a little bit hard to see, but this is kind of a summation of an inspection report where you see these blocks here. That means the inspection was overwhelmed by nuisance defects. When we pre-render our database, you see in that case, most of the mask is able to be inspected. So at least we can take it to the next step. So that pre-rendering using a model-based inspection situation allows us a much more efficient way to get the mask inspected, especially for early prototyping, development work, and very complex designs, such as the one shown on this. So now we've gone through a couple examples where we used image quality to do contour-based simulation to improve RET. We used it in source mask optimization to get a better convergence. We've used it for improving mask process correction. And then we've applied it in a kind of a virtual model-based mask rule checker, not just for writing and patterning, but also for inspection. So it sounds interesting. Maybe this is a powerful tool that can be used even more so as mask complexity increases and we get to more 3D effects with EUV and those sorts of imaging situations. So the question then is, are there any bottlenecks to a broader deployment of image quality as a tool to tie mask making and mask pattern fidelity to wafer imaging? And those who've been doing this for a while kind of know this, but I'll state it anyway. When we're working on patterning advancements, usually there's kind of a pendulum swings back and forth between metrology and mask making. So it's kind of a tug of war. If you measure things really, really well, you can tell that your mask writing step is compromised. If your mask writing step is far beyond your ability to measure, then your real bottleneck is in the metrology, your ability to characterize. And since multi-beam mask writing has kind of come onto the scene for mask making, especially with high fidelity resists, high dose, high fidelity resists, our ability to create a pattern on the mask now far exceeds our ability to measure it. So I would argue that one of the main bottlenecks in capturing image quality in more of these patterning-based flows is our ability to accurately characterize what's going on in the mask, especially for complex 2D shapes, small shapes that the multi-beam mask writer is capable to do. And this just shows a simple graphic of that. You have a mask pattern with lots of little scatter bars. This is what the mask looks like. This is right near a cliff of imaging, so you see some of these scatter bars don't resolve very well. That might be important, it might not be important. In order to understand the image quality of this mask and use that information in subsequent steps, we've got to be able to measure this. And that is a limiting case now in adapting image quality metrics to a broader set of use cases. So how big a problem is that? So this is a very simple graphic that hopefully illustrates that. This is a bird's eye view or a very high up view of an advanced layer mask. I think it's a contact layer. And this just shows where the patterns are, the density of the patterns are. There's really no pattern fidelity information in this. This is just the layout of the mask and how there's a lot of concentration of patterns here. There's not many here, but there's a wide range of shapes with tons of features and 2D structures all over this. So we really would like to know what's going on across a much broader set of structures here than some test cells or hundreds of points. And so what do we really need to do? If we want to build accurate image quality based models, and we want to really understand the image quality content of this mask layer, we need dense, high resolution metrology of these complex shapes. And just to give you an idea of how far we are from being able to produce that sort of measurement structure, it would take roughly, in this particular case, about 100 hours to measure a 1 millimeter by 1 millimeter patch at sufficient resolution to contour at 100%. So we are nowhere near being able to produce the richness and amount of metrology data to start building very comprehensive 2D contour models for more complex designs. So, net there on the metrology side is one of the bottlenecks to doing more with this technology is we need more data at higher resolution, wider area metrology, ability to faster, more rapid contouring of shapes, and the ability to calculate full field image quality of the mask, where we can really assess its capability. We can build models. We can inject it into MPC flows. We can inject it into writing rule check flows, use it in optimization and also convergence for things like ILT. And we had a little taste of wide area metro for a project we worked on with IBM some years ago. Here's a pattern wide area. This was be able to measure over multiple microns in one frame, multiple microns square. We had a high-speed image contouring algorithm, which allowed us to contour over those wide areas very quickly. So you see metro turns into image quality map. Then from that, we're able to calculate at fairly high resolution and high frequency a pattern shift map of the mask patterns. And we're also able to calculate frequency maps. So the design has a certain spatial frequency content. You really would like the mask to reproduce that. And what you see here, when you have this kind of data density, you can see that frequency components you actually don't want are injected into the mask. And those are going to obviously propagate to the wafer under various conditions. So this gives a little bit of a taste we had for wide area, very dense metrology, and how through image quality maps, you can get much more information and use it and feed forward. So the summary then, I'd like to go back to the title, which was Know Your IQ. Here, I'd like to emphasize know and use your image quality is a very interesting and important thing, at least we believe in mask making. We reviewed the importance of mask image quality by applying a 2D mask contour to hotspot correction, MPC and OPC, to characterizing defects a little more carefully, doing co-optimization, building models, and doing this pre-rendering of the database to improve the quality and speed of inspection in very complex mask flows. We do believe mask and litho can be tuned for better performance by embedding more mask image quality content into the convergence flows. Mask shape transfer models, which we talked about here, allow us to accurately predict image quality, which can be used in a lot of things. And the key to getting all three of those more widely used and more powerfully enabled is in addressing the metrology bottleneck. It will further open a lot of doors. And unfortunately, well, I don't know about unfortunately, but multi-beam has kind of shifted now the burden onto the metrology people to kind of raise the bar, raise the game on speed, accuracy, and the ability to capture 2D image content on a mask much more efficiently than today we're able to do. So that's what I'd like to share with you today. I hope you found it interesting and worthwhile. And that's our views on knowing and using your IQ for masks. Thank you.